Hello guys, let's do another lecture. This one I want to, it's almost like a review and also push forward of our next section where we're going to use principal virtual work for finite element or matrix structural analysis, whatever you want to call it. I'm going to go through to summarize how we get here. Alright, at the beginning of this class, this is the matrix structural analysis. We understand that for any system, if you can get element stiffness matrix, then assemble the matrix into a global stiffness matrix, apply boundary condition and external loads, and then apply loads, solve it, and doing post-processing. Those are easy. I mean, not too bad. The key is to actually get your EK. Not just get EK for the bar, for the beam, or for the frame we talk about. To get EK for anything. In fact, I actually told you the EK, by definition, it's actually really easy to do. For example, let's just say you have some funky element. I don't know why you have to do something like that, but maybe this element is just a blob, and you're building a castle with this blob, and then you want to apply force and know how much your castle moves. Great. Matrix structural analysis or finite element analysis is gonna get you there, but you need to define your element first. So to do that, this blob is a continuum. What you need to do is to define a couple of loads. I don't know how you're gonna do it, but maybe you can define 1, 2, 3, 4, 5, 6 nodes. It's a 6 nodes element, and also it's kind of funny, the nodes doesn't have to be on the edge. Some elements, they actually have nodes right in the middle. It doesn't matter. The ability of doing a node in the middle give you the ability to apply loads or boundary condition in the middle of an element. But it doesn't matter. Once you define it, say if this is a 2D element, all you have is the degree of freedoms. 1, 2, 3, 4, 5, 6, 7. So this is a 14 DOF element. And then so as a result, the EK will be a matrix that is 14 by 14, right? We talk about it. So how you're gonna organize it? You're gonna organize it like this is the 1, 2, 3, yeah, whatever. You got x1, y1, x2, y2, something like that. And we know that if you time the stiffness matrix with displacement, you're gonna get a force. fx1, fy1, all that type of stuff. Then we talk about the definition of this is that if you if say you keep this guy x1 equals 1, but everything else is 0, then you do the time thing and go through the matrix. What do you find out? That what you're gonna get at the force will be exactly the same as the first column of your stiffness matrix. K11, K21, so that kind of provided us a way to be able to physically find element stiffness matrix. So basically, if I can take this guy and fix all the coordinate other nodes, just fix it, and then you have to fix everything. And then on the node number 1, you're going to fix it in the y direction, and then now you're going to apply some force, which you don't know what, but you will say, okay, I'm going to apply a force, and then I will force this thing to move 1 here. Okay, I'm gonna force this element to move as 1, 0, 0, 0, 0, 0 all the way along. And if you can find a way to find out how much this force is, and what is the reaction forces on each one of those to hold them at 0, you essentially have all those forces by definition, and at the same time you have the first column of your stiffest matrix. And then you can actually redo that process by holding everything but the second degree freedom to be 1 and all other things 0. Then you get a second column, third column for So basically the idea is that if we could the problem of trying to find the EK becomes the problem of trying to find try to solve a system, which in this case an element in equilibrium. So basically the problem becomes if I have something and then I know their boundary condition, it's all fixed and everything, you know, you got the idea, it's all fixed. Then I'm just like gonna like pull this thing with a certain force P, and how much this thing moves. Because this thing is supposed to be linear, right? And then if you add a P, maybe it's equals to 10 pounds or 10 Newton. Then you find out that this is like 0.01 meter, whatever. If you want 1 meter, you just magnify it by 100 times. That's easy. And also the reaction, then you're all set. Okay, so we did that for a bar and for a beam because they're all quite easy. In our previous classes, we didn't use principle of virtual work. What we did use is mechanics of material, some structural theory, some statics. That is because those guys are easy. But now, if you're handling an element like this, you have to do principle of virtual work. Why? Because principle of virtual work, it is very flexible, and then it is very robust. I wouldn't say the math is very easy, not easy in math. In here, I mean, not easy in math, specifically, it's like two aspects of it. The first one is like you need to come up with a very clever assumed displacement function. That's kind of tough. I mean, like in 2D, you need to come up with u, x, y, and v, x, y. In 3D, I don't want to even write it. It's like u, x, y, z, v, x, y, z, and w, x, y, z. Okay, not very straightforward. You have to be clever in doing that. The second aspect is that there's a whole bunch of integrals, right? In fact, it's the integral over volume. We already know that, and then we kind of in our examples, it's a beam. I mean, come on, we derived it. There's only one stress element, which is normal stress. So there's like one term in the integral, but still it's such a pain. But conceptually, it's doable, and it is very powerful. And then what do I mean by like robust? Robust means that it will always give you an answer. So this is pretty important because, I mean, frankly, just look at this guy. If I'm telling you I'm going to be able to get a displacement function for this guy, you probably won't believe me. No, I won't believe myself either, because for the most part, when things get this complicated, the best you can do here is some approximation. But the beauty is that principle of virtual work, it will if you give it an approximation, they'll give you an approximate answer. That's another, if people are in mechanics, they start talking about some jargons to you, you don't understand, they call it wake form. What does that mean? It is the wake form of equilibrium equation. So we're back at the beginning now. For a thing like this guy to satisfy all the equilibrium equation, that means at every single point in this body, you have to have, sigma f equals 0 and sigma m equals 0. Teeny tiny little bit, like you cut anything out, this need to be satisfied continuously across everything. But if you really just try to solve that, there's no term as strong form, but I'll say this is a strong form or closed form or whatever, or explicit just strong form, or someone call it explicit solution. To do this, you need to find such a beautiful function that will satisfy everything, so that this is not violated by any means within any part of this body. For the most part, this is not possible. But the principle of virtual work, wake form, that means you can have something, you don't have to satisfy the equilibrium at every single point, but what it enforces is that the overall energy of all your stress, strain, and external force, on the energy level, the deformation, everything should be in harmony, so that virtual displacement or virtual deformation does not result in any work. So that's why it's called a wake form. Sometimes it's also called a variational methods. That's variational, means our little delta, which is actually take a variation of the displacement function. Long story short, you don't need to understand all that, but just know that to develop a generalized way to derive EK, principle of virtual work is really needed. The thing neat about this guy is that once you make a few very basic assumptions, like this, you assume it, and then you set it up in a certain way, all you need to do is just follow steps. So, So basically, the principle of virtual work is a very easy to follow procedure. We're gonna show you guys in the next segment of this class, which will contain probably 5 or 6 lectures, that by setting up the displacement functions in a particular way, principle of virtual work will give us EK for any element automatically. So you just need to set up displacement function in the right way, and apparently, as you have seen how sensitive our solution is to displacement functions. I hate to tell you, but if your displacement function assumption sucks, your element's gonna suck. Okay, There's no way around it. The way we're gonna learn it, we're gonna learn some like classic way to set up some discipline functions. We're gonna, go with the bar and the beam. We're gonna kind of redo those, and then you'll see the beauty of this. And at the end, we're gonna use this to derive a 2D element, which it's like the simplest 2D element you could ever imagine. It is called a constant string triangle. Yeah, then that'll be the end of this class for derivation. Yeah, we'll see how far we can go, and we'll see how we get there. Okay, see you next time.